Have you ever wondered how cold or hot space is? It's a question that probably tickles the minds of many. You may think of space as a vast, frigid void, or perhaps a fiery furnace of stars and galaxies. Today, we're going to unravel this cosmic conundrum in a way that's easy to comprehend, no matter your background. So sit back, relax, and prepare to venture into the great unknown. Get ready to embark on a cosmic journey to understand the temperature of space. Before we dive into the temperature of space, let's define what space is. Space, or outer space, is the vast expanse that exists beyond the planet Earth and between celestial bodies. It's a nearly perfect vacuum, with only a smattering of particles scattered across vast distances. Its vastness is hard to comprehend. It extends infinitely in all directions, far beyond what our eyes, or even our most powerful telescopes, can perceive. In this boundless void, there are no atmospheres, no air, and no weather as we know it on Earth. Space is a realm of emptiness, silence, and extreme conditions. But despite its emptiness, it is the home to everything we know: galaxies, stars, planets, and yes, even us, Earthlings. Now that we have an understanding of what space is, we can delve into its temperature. Understanding the temperature of space is not as straightforward as it seems. Why, you ask? Well, that's because the concept of temperature as we know it on Earth doesn't exactly translate to the vast, infinite expanse of space. On Earth, temperature is a measure of the energy of particles. The more energy these particles have, the higher the temperature. We feel temperature as heat or cold based on the energy transferred to us from these particles. But in space, things work a little differently. You see, space is mostly empty. With fewer particles to collide with, the concept of temperature becomes a bit nebulous. It's like trying to measure the temperature of a single grain of sand in the middle of the desert. Without other particles around it, does the sand grain have a temperature? In a similar vein, the temperature of space isn't the average kinetic energy of particles, as it is on Earth, but rather the energy of the individual particles that are there. And here's another wrinkle. Space isn't uniformly empty. Some parts of space are denser than others. Near stars, for example, there's more matter, and thus more energy. Far from stars, space is emptier and particles have less energy. This means the temperature in space is not uniform, but varies depending on where in space you are. Furthermore, the temperature of space can also be affected by cosmic background radiation, the afterglow of the Big Bang. This radiation permeates all of space and has a temperature of about 2.7 degrees above absolute zero. But again, this is not a temperature in the traditional sense, but rather a measure of the energy of this radiation. So when we talk about the temperature of space, we're really talking about a complex mixture of factors: the energy of individual particles, the density of matter, and the influence of cosmic background radiation. Each of these elements contributes to what we might consider the temperature of space. So, the temperature of space isn't a single definite number. It's a fascinating puzzle that continues to challenge our understanding of the universe. Space, though largely empty, has extremely cold and incredibly hot regions. This paradox might seem confusing, but it's simply a testament to the vastness and diversity of the cosmos. Let's start with the chillier side of things. The coldest parts of space are not, as you might expect, in the vast, empty voids between galaxies. Instead, they're found in the afterglow of the Big Bang, known as the cosmic microwave background radiation. This radiation permeates everything, everywhere in the universe, and has a temperature just above absolute zero, around 2.7 degrees Kelvin. That's colder than anything naturally occurring on Earth. But what about the warmer end of the spectrum? Here's where things really heat up. Stars are the obvious hotspots in space. Our own sun, a fairly average star, has a core temperature of approximately 15 million degrees Celsius. That's hotter than anything we can create on Earth, even with the most advanced technology. And yet, stars are not the hottest things in the universe. That title goes to supernovae, the explosive death throes of massive stars. For a brief moment, a supernova can outshine an entire galaxy and reach temperatures of billions of degrees. But wait, there's more. The cores of galaxies, where supermassive black holes reside, are another hotspot. The material swirling around these black holes can reach millions of degrees. And let's not forget quasars, incredibly bright and energetic objects that are believed to be powered by black holes at the centers of distant galaxies. They are some of the hottest and most luminous objects in the universe. So, from the icy cold depths of the cosmic microwave background radiation to the searing heat of stars, supernovae, and quasars, Space is a study in extremes. It's a stark reminder of the incredible diversity and complexity of our universe. As we can see, space's temperature varies greatly, from the extremely cold to the incredibly hot. The cosmos is a place of stark contrasts and breathtaking extremes, a testament to the immense power and profound mystery of the universe we inhabit. You might be wondering, how do astronauts survive these extreme temperatures in space? Well, the answer lies in the exceptional engineering of spacesuits and spacecrafts. These are not just any run-of-the-mill outfits or vehicles, but meticulously designed technological marvels that shield astronauts from the harsh realities of space. Consider the spacesuit. It's not merely a snazzy outfit, but a personal life support system, a mini spacecraft if you will. Its layers are designed to provide everything an astronaut needs to survive. The outermost layer is made of a material that reflects the sun's heat and resists micrometeorites. Beneath that, there are multiple layers of insulation and a cooling garment to regulate body temperature. The suit has a ventilation system to provide fresh air and remove carbon dioxide, and it's pressurized to keep astronauts comfortable in the vacuum of space. Every detail, right down to the gloves and boots, is designed for maximum protection and functionality. Now let's talk about the spacecraft. Spacecrafts are like houses for astronauts in space, only with a much better view. These vehicles protect astronauts from the extreme cold and hot temperatures of space, harmful solar radiation, and the vacuum of space. The spacecraft walls consist of multiple layers of insulation and shielding. The outer layer reflects solar radiation and protects from micrometeorites, much like the spacesuit. The inner layers of insulation maintain a comfortable temperature inside the spacecraft. The air inside is carefully controlled to provide the right mix of oxygen and nitrogen, just like Earth's atmosphere. Furthermore, the spacecraft's systems continuously monitor and regulate the temperature inside, using heaters and coolers as needed. They also manage humidity and remove carbon dioxide, creating a livable environment for astronauts to work and live in for months at a time. So as you can see, surviving in space is not a matter of luck, but a testament to human ingenuity and technological advancement. Thanks to modern technology, humans can venture into space despite its extreme temperatures. So let's recap what we've learned about the temperature of space. Firstly, we delved into the complexity of determining the temperature of space. It's not as simple as sticking a thermometer out there and reading the numbers. Space isn't like our earthly environment. It's a vacuum, devoid of matter, and thus doesn't have a temperature in the way we usually understand it. Instead, we measure the temperature of space by the energy of the particles, the cosmic microwave background radiation, and the interstellar medium. We discussed the cosmic microwave background radiation, the afterglow of the Big Bang, which gives us a universal average temperature. This temperature is a chilly 2.7 degrees above absolute zero, or approximately -270 degrees Celsius. That's colder than any temperature ever recorded on Earth. However, space isn't uniformly cold. We explored the coldest and hottest parts of space. The coldest place we found is the Boomerang Nebula, where temperatures drop to an unimaginably frigid 1 degree above absolute zero. On the other hand, the hottest regions are found in galaxy clusters, where intergalactic gas reaches a scorching temperature of millions of degrees. Then we turned our attention to how astronauts survive in space amidst these extreme temperatures. Spacecraft and spacesuits are marvels of engineering, designed to protect astronauts from the harsh conditions of space. The International Space Station, for instance, has insulation and temperature control systems that maintain a comfortable environment for the astronauts aboard. Spacesuits, too, are equipped with layers of insulation and cooling systems to regulate the body temperatures of the astronauts. The temperatures in space can vary vastly, from unimaginably cold to scorchingly hot. But one thing remains constant: our human fascination with the cosmos. We continue to explore, to learn, and to push the boundaries of our knowledge. In wrapping up, we've taken quite a journey today, from the coldest corners of the universe to the hottest, and even into the workings of a spacesuit. We've learned that the temperature of space is a complex concept, determined by a variety of factors and not as simple as it might seem at first glance. So, the next time you gaze up at the stars, you'll have a deeper understanding of the fascinating world beyond our planet.